want to draw it between.
Hold it over here.
Alright? So that one is 1 meter. Now, all I want to do is define some function x, some function y. Alright? So again, 5 steps. The first step is system. Our system definitely is the entire cylinder. So that's my system. And then step 2, draw a FTD. FTD, if I want to draw it, it's just the if I take an element here, let's take the green marker here, and if I take an element here, alright, and on this element, there is only the pressure force, the normal force. There is no tangential. Why? Because it's not rotating, we mentioned that. There is hydrostatics, there is no velocity. That means, therefore, there is no shear stress. Therefore, the only force is normal force. So all I need to do to draw a FTD for that, so instead of drawing for infinite number of elements by FTD, I just take one of these elements, right, and draw a FTD for that. And I'll look it from here. So I look it from the side. So I only see this cylinder, just a circle. I don't see the gaps. And my part of my system that I'm trying to do FTD is going to be just arc length, right? So you look it from the side, so you don't see the depth, you only see the ds, the arc length. And the pressure force on that is acting this way, dF. The infinitesimal force that is only related to pressure, not shear stress. Right? Now, if you take cylindrical coordinate, you're still in part 50D. This is going to be your theta, and then this is your d theta, and this is your ds, and the area of this tiny element, dA, is just estimated with the ratio. So it's going to be this side 1 times this. So it's going to be 1 the span times ds. But what is ds? 1 times, what's ds?
R d theta.
R d theta. So the area is R d theta because the span is 1, right? So, and also dF, because I just said it's only coming from the force, is equal to P dA. I'm glad they have it so much. I hope they will. dF, yes, P dA. Alright? And what is P at this point? At this point, you got a height, alright? It's not H0. H0 is the height from the central cylinder. We're talking about the height from this element to the surface. So that's your H. So if you look at it from the side view, if that's the H, this is the surface, right? This one from the center to here is what? H0. But the one I want to put in the formula for pressure is this height. Right? So for P, I say gamma or rho G or gamma times H. This H times dA. That's your dF. Right? But what is my H? Look, this H is equal to H0 minus, right here, H is equal to what? H0 minus this value, right? You agree with that? You subtract H0 by this value, you get H. So H is equal to H0 minus, and what's this value?
R sine theta.
R sine theta. So H0 minus R sine theta is your H. Plug it in here, so you're going to get gamma for H, you get H0 minus R sine theta. Gamma H dA. applying this definition. R d theta. So you're gonna get gamma, and for H you get A0 minus R sin theta, and then for dA you get R d theta. Why? Because the span is 1. So that's what? That is the magnitude of EF, is the magnitude of this vector. But what I want to find in this homework, or problem, is to find some resultant or sum in the X and resultant in the Y. Right? Okay, so if I want to find sum in the X, what do? First, I need to get the X component. What's the X component of that? Break it down into X and Y. So that's the X component. I need to use the red here. Never use red. So that's the X component going to the left. So that's dF in the X. And the Y component going down this way, dF in the Y equation. So dF is what? dFx is what? dF in the X is what? dF times this angle is what? Theta. You see, this is theta. Therefore, this angle is theta. So dF, the magnitude of dF times cosine theta is equal to dFx. I'm missing something. Can you tell me? If your y axis X and Y is this way, that's what I draw, right? I put it here. Put it in the center. Put your axis here, X, Y. Then the X component acting on that element, dFx, is dF cosine theta. But something is missing here. Can
It
you
should
tell
be
me?
negative.
It should be negative, right? Because it's going, you see the X component going this way. So there is a negative here. So all I need to do in order to find the resultant X is equal to what? I have to sum them, right? So the F resultant in X, which is actually sum of this, which is integral of dFx, is equal to. Just take the integral of this. So you get integral, just use a little color, integral of negative dF. What should I substitute for dF? Gamma H0 minus R sine theta R d theta. Gamma H0 minus R sine theta R d theta. That's for dF. So negative dF times cosine theta. Sum of this from where to where? Theta is equal to 0 to pi, because we're going to do full circle. If you do half circle, it goes 0 to pi, not to 4. Yes?
When you wrote it on the board Monday, you did FRY, and so it was like the same equation except it was sine theta at the end. Which one did you want us to?
I didn't quite understand. When I did it last class, what did I do? That's fx, and then fy is going to be sine.
Yeah, I believe you did the FY portion. At least that's what I have a picture of. So.
Yeah, the reason for that is because I asked you the intuition. Well, in the x, according to the intuition, is 0.
Yes.
But they cancel out, right? But in the y, because you have a pressure difference in the depth, it's going to be net in the y. So we try to just find the y because we have limited time. Because they end up like, well, right now I want to do both x and y. Now, if you submit it just for y, that's fine.
Okay.
I'm not going to deduct from it. So here, let's compute this integral. What do I get? For this, I expanded negative gamma h0 integral. I also have this. Now, here is the thing. You can see that. Look at this integral. This integral is over theta. We don't have integral over r. So what can I do with r? I can take it out, right? It's constant. Another thing is, sometimes we have over r and then over theta and over z. So we may accidentally get confused and say, well, this is not the function of, for example, if this is z, right? and then R is here, and this is over R. We may say, well, this is only Z, we may take R out, right, to do it with R. But look, if R is a function of Z, how can R be a function of the radius to the function of Z? The code problem in the homework. We can't take it out. Even more sophisticated mathematicians, they make this mistake. They say, well, this is R, you can separate it, bring it to R, right? But you gotta be careful. Whenever you can take it out, that is not a function of Z. So you better keep everything inside the integral before simplifying. That's the point. Just simplify the very last one. Okay, so here you get, let's use this one. You get minus gamma H0, take it out, and then you have R d theta cosine theta from theta 0 to theta is equal to 2 pi. And then plus, I write the rest of it here, integral sine theta cosine theta from 0 to 2 pi d theta. And then only sine and cosine remains there. You get R squared, and it's positive. So positive gamma, R squared. Positive gamma, R squared, sine, cosine. Well, you can take R out, right? D theta, and the first one give you negative gamma, H0, and then you can also take R out. Well, you can take cosine. You can take R here, but you can't take cosine, because cosine is functional. Now look guys, this is what? The initial function for that. You can't substitute 0 and 2 pi into cosine. I got a question from another student after the class that if you put 0 here, 2 pi cosine 2 pi minus cosine 0, well, this is not the initial function. You remember the calculus, basic calculus? You gotta find a function that if you take derivative, you get cosine theta. What's the function you get derivative, you get cosine theta? What's the initial function for cosine theta?
Sine.
Just sine theta, not negative. Take the derivative of that, what do you get?
Cosine.
Cosine theta. So you evaluate that from where? 0 to 2 pi. What do we get?
0.
0. So this guy is 0. It looks a little bit scary, but it's 0. What about this guy? What can you write for this? This, you can write 2 sine 2 theta. How did I do that? Table of trig relation. You don't need to memorize. If you have it in memory, that's fine, that's good. But when you reach equation like this integral is given in the table of integrals. So you Google it, table of integrals, and it's going to give you a bunch of tables. Then you can just get this integral right off the bat. You don't need to waste your time as an engineer. Right? But another way is to get trig relation. So if you expand that, I'm sorry, this is 1 over 2. If you expand that, this is going to be 2 sine theta times cosine theta. You multiply by 1 over half, 1 over 2, you get sine theta times cosine theta, this. So these two are same. This one and this one are same. So what's the integral of that? If I take the integral of that, what do I get? Take 1/2 out. What's the integral of sine 2 theta? 1/2. What's the integral of sine 2 theta? Cosine 2 theta, but you need a negative, right? Don't believe it? Take the derivative. Derivative of that is going to be negative 2 times sine 2 theta. Cancel out with that, and then you get that. So that means the initial function is this. So put the bounds. If I evaluate that from 0 to 2 pi, what do I get? I get cosine 2 times 2 pi, 4 pi, minus cosine 0. What do I get? 1. 1 minus 1 is what?
0.
So this is also 0. And then you may say, well, I think I screwed up. But look, what's the resulting force in X?
Nothing.
Nothing. So it's exactly agreeing with our intuition. Whatever you get from math, you gotta match with the real world, with the physics. If it doesn't match, something is wrong. Now, the other important part is summation of force in y. So this guy, in your homework, you just put 0, and in your y, what do you put? In the y direction? As I mentioned before, I'm not really interested just to see the final answer. I'm interested to see your derivation answer. So for the y, I already have my three steps out of 5. So step system, I already did my system. FTD, I already did. This is my FTD. Equations. Out of this equation, I already did some force in x0. Some force in x. I don't say it's 0 yet because I did a constraint. If you put a constraint here, like a cable, and you hook it up with a weight, then when you constraint it, then you can say 0. This should be in equilibrium, so it's 0, and then you can find all the force in the cable or whatever. Well, I just said find the resultant force, right? So in this step, we just got that. What about y? And what about moment? Right? There are 3 equations in 2D. So now I want to work on that. Okay? Summation of force in y is just simply integral of df but in y direction. You see that this force? We did the summation in the x, so it was integral df cosine x. So I say df y. What should I put for df y? df time? df time sine theta. Positive or negative? Negative. Integral of this and theta 0, theta 2 pi. Again, the same token, you already have your df is that, just plug that into that integral, so you get integral, take that negative out, negative integral from 0 to 2 pi, df sine theta. For df, I put gamma h0 minus r sine theta, gamma is 0 minus r sine theta minus r d theta. This is df, but we need it out, and then sine. Now I need to evaluate this integral. How do I do that? Exactly like that. Just expand it distributed. So for the first one, you get negative bring gamma is 0 out, gamma is 0. And also you're gonna get r out integral sine theta equals 0 to pi. And then for the second one, you're gonna get negative, so negative positive, bring gamma r squared and integral sine theta squared, because you're going to get sine theta here, d theta from theta 0 to pi. Double check it before we proceed. Negative gamma h0 r yeah, this sign of whether we here inside this sine theta, and then I put d theta here. And this is more easier to understand. So negative gamma is 0 r sine theta, gamma is 0 r sine theta, right? And then the second one is going to be, so we can bring this negative here, positive here. The next one is going to be positive. Gamma r squared sine squared, gamma r squared sine squared. That's right. That's right. Okay. So this guy, what do I get for sine theta? What's the initial function for sine theta?
Negative cosine.
Negative cosine. Take the root of that, you can solve it. From 0 to pi. What do I get? 0. You guys did the homework, right? Okay. So you get this guy is 0. And then you may get confused. This one thing that happens to all of us. It's the most frequent mistake. You may say sine theta 2 pi 0 minus 0. So this one is also 0. Right? Don't say that. Because you all say it. Don't say it. Don't say it. Just find the initial function. This is not the initial function. What's the initial function of that? What's the integral of sine theta squared d theta? One way is you are a freshman, undergraduate, and you already have a calculus, so you can just start from scratch and get the integral. That's one way. Another way is you're not a freshman, undergraduate, and you forgot the method of integration. And you are an engineer, you're not a mathematician, so what do?
Look it up.
Table of integrals. So that's what I'm going to do right now. In fact, honestly, I forgot it. So I said integral, Google it, integral of sine integral int sine theta squared. With respect to, you can use makers, you can Google it. So here, you can either grab that, there is a book written by, this is the oldest school. The oldest school, they didn't have Google, they used to do this. This guy, on the beach, this guy, he wrote a book called Table of Mathematical Relations, and it was like this thick. So the people, old school people, engineers, they did not have Google, so they use that book and go to that page, and all these integrals are in that book. Not even one single of them is fixed. And they just copy paste it from that, the initial functions, right? Now we have advantage of having Google, so this poor guy, he can't even sell his book anymore. And he passed away like 50, 60 years ago. Like this is long time ago, 1800, 1890, so he born 1890. All right, so integral of sine the square d theta, according to Mr. Google, I get that. And if you don't believe it, go ahead and do it yourself. Take the derivative of that. So this one, according to Google as well, is theta over 2 minus sine 2 theta divided by 4 plus c. Now, if I give this problem in the midterm, I'm going to give you also table of integrals. So in the appendix, you're going to have that. You don't need to do this integral. The challenge in this course is not calculated. The challenge is problem set up. How you set it up, right? So using that relation for that, let's evaluate it between 0 and 2 pi. So if I evaluate that between 0 and 2 pi, what do I get? I get 2 pi the other end. 2 pi, put 2 pi here, so 2 pi over 2. And then sine 2 times 2 pi, 4 pi. What's the sine of 4 pi? 0. Minus, and there is also c, but when we do upper minus lower, this c disappears. It's definitely bigger, right? So if you put 0, what do you get? 0, 0. So the result is what? 2 pi over 2 pi. So that means this guy is not 0. Intuitively it was 0. When we first look at it, it was 0. Why it's not 0? When you do the correct integration, you get pi. So let's assemble it together. This guy was 0. So that's going to be 0. This was 0 plus gamma r squared pi. So I'm going to just write the final result here. Some force in y is what? Positive. It's not negative. It's positive. Pi r squared gamma. Is that right? Pi r squared gamma. Right. Okay, now guys, what does it say? Is it acceptable? As an engineer, you should always check it with experiment. Well, we know the x is always 0, right? But what about y? Some of you guys may have heard of a guy called Archimedes. I can't write his name, but this was a guy living like 2,000 years ago before Jesus. Like this was ancient, like pyramid, that kind of thing. And this guy, everybody thought he was crazy and insane, but he was not. He was very smart, and he was so smart that a person bring a gift for the king, and he said, "Well, this is the crown, and it's made of 24K gold, like 100% gold." And there you go. And the king was a little bit suspicious. And he said, well, maybe inside it is steel or iron. It's not like gold plated. How can you know that, right? And there was no way to know it except to break it down, right, and just destroy the gift. And the king didn't want to do that. So the king called this guy Archimedes and said, can you tell me if this is the real deal or gold plated or not even gold at all? How can you tell me? And this guy had enough time, unlike us. We only have like 10 minutes, 5 minutes, 22 hours, 1 day. We have always deadlines in projects, right? He had infinite time, so he took his time. I think it was like almost a year. And one day, he even took the crown to his home. So one day he was playing with that in the bathtub. It's a real story. It's not a joke. It's a real story. And he realized that crown, what if he could have pure gold with the same volume? Like if it was made of gold, the same thing, in the same bathtub. What would be the weight? If there is no weight difference, that's made of pure gold, right? So by doing that problem, he realized how much force is imposed on the cylinder, which is basically the crown, from the water. And the relation he got is very interesting. He said the force is equal to the weight of displaced water, not the weight of this object, not inside the object. So it doesn't matter what is inside of that. The weight of displaced object. If I put this in the water, if I fully submerge it, how much of the water is displaced in the volume? What's the volume of displaced water? Can you tell me?
Volume of the cylinder?
The volume of cylinder. What's the volume of the cylinder?
Pi r squared h.
Pi r squared times h. That's right.
Or no,
what's my
h?
h?
1.
So it's pi r squared, the volume. Right? And Archimedes said the volume of displaced water, that means if you have the volume of this, which is pi r squared, then you multiply by the density of water, not the density of that. And that's the force that water applies to the object. So what should I multiply that? You see that? You have this multiplied by gamma, right? Gamma pi r squared. That's the force that water applies to the object. Because this gamma comes from water. It doesn't come from gamma object. Object also has gamma. Here we get the same result. We got the same result in calculus. So this comes from Gauss. This guys come from the modern math, the calculus, the Gauss, right? Riemann, Gauss, all these guys in the last 200 years. This comes from the crown. This comes from 2,000 years, 2,500 years ago. But they exactly match. We did exactly 2 independent paths, and we got the same result. Now, I want to, before we do the tour, I want to give you a meter waiver. Right? I want to give you a meter waiver. And this meter waiver is really easy to do that. And it depends on if you have looked into, let's see if I can log into this computer. What do you have? slides. The very last slide. Did you see the very last slide? Did you work on it? I think one or two of you have, because I got an email, a question about that. Now, if it happened that you already worked on it and got some numbers, you're just ready to submit your user paper. But if you didn't get that, that's fine, because I'm going to solve it hopefully right now myself. But just like last class, I'm going to solve it 100% just like this. I'm going to solve, make FDD half rate, and then give you the homework, next homework for you to solve it. But before I do that, do it a meter waiver. Alright, for people who did practice at home, exceptional people who did it at home, and they got some numbers, why not they submit them in meter waiver? So next time, if I do the slide, make sure you go through it, because I'll probably make a meter waiver at some point. And if you already do all this slide, you can get a waiver. This takes forever to load. You know, that's the reason nobody uses Windows. In all those computers you're going to see today as a part of this tool, nobody ever uses Windows. In none of those computers, Windows is installed. None of those computers, Mac is installed. Why? Because Mac and Windows, they're not operational for hard number crunching. When you do huge problems, like let's say you want to solve this computation, and this also rotates, this cylinder rotates, and it's bouncing up and down. So it causes the fluid to bubble like that, you see? Those problems they require billions and billions of equations. And that requires a huge number crunching. For those systems, this thing is just toy. Windows, nobody uses Windows. Windows is only for gaming. So all those computers you're gonna see in the tour, they're all Linux computers. Nobody uses Windows. Alright, so here, let's go to this course page. Is the problem, and I wish I could download it and
Damn gate control system.
hopefully they have some here because they don't very much yet. I'm gonna make it full screen. Still doing well. You can do it full screen? You have to teach me how to do this. I don't know. I accept whatever you say. So that's a meter waiver. If you can just give me the answer, the numerical answer, matching 3 significant digits in less than 5 minutes. Not even 5 minutes, less than 3 minutes. You know, you know that this is almost impractical, right? It's just ridiculous. So that's the reason that I'm doing this is because I want to make meter waiver extremely hard, unlike my vector static class that is possible that you get a meter waiver. for this class, you only get a meter waiver if you are that single guy, a very exceptional, bright nerd that did all this at home without even asking for it. So can you imagine that guy? That, you know, I've seen people like that. Even teachers don't ask if they do it themselves, like they take credit. But those people, they deserve a meter waiver. They really do deserve it. So that's what it's gonna say. Now, but work on it. Maybe you can get. I mean, it's not hard. It's 3 lines. This is 3 lines. In 3 lines, you can get the result. Okay. While you do that, I'll go to the basic. Remember 5 steps? That's what I want to see. When I grade this, I want to see your 5 steps. And what it asks, it says, when you see that mechanism, block pulley system, cable pulley system, that convert that load into like factor, so it's a multiplier, right? That causes the gate over. You see that L-shaped bend mechanism right here. I'm talking about this mechanism. This is connected to this cable, and imagine all these pulleys are frictionless, massless, except the only mass is right here, the block. Now, you can see that if you apply weight here, this multiplier is going to increase the force in this cable, and this is going to cause this arm to rotate counterclockwise, so it comes down, and then it's going to rotate this door, or this gate. You see, this is the gate. It's hinged here, it's fixed here, but it can rotate like this. So you can open it, and you can close it. And you can see that behind it is a dam, so you got all these features here. But at some point, you're gonna open this gate and let this water go, depending on the water level. You want to control the water level. So at some point, you have to open up and close that. And how do you do that? You just add in blocks here, right? So this problem is asking how much of the weight should you put in this block, in this, in this location, such that it causes this gate to stay in equilibrium. So nothing is moving, everything is equilibrium. Obviously, if I have just a tiny value to that, it's gonna cause this door to push a little bit further, and if I remove that weight, it's gonna cause this door to open up just a little bit further. So we're just trying to find that sweet point. The point of equilibrium. Alright, so the way I do that, I do 5 steps. So this is the way you set up the problem. You choose your system. How many systems do you want to get? What's the maximum number of systems you can get? Can you tell me who's there? Maximum number of
Is it
systems.
3?
Huh?
Is it 3?
No.
Oh.
You can make as many as you want, couldn't you?
Yeah. What I'm saying is, what's the maximum possible number of systems? Yeah, I know that 3 is probably the best choice. That's a good strategy. But
Yeah.
what's the maximum possible number of systems?
6,
6.
7,
So you said 6.
6 or 7.
You said 8.
8.
You said 8.
Yeah.
Okay. So let's do 6 and 8. So if you take this as system 1, this pulley 2, this one 3, 4, 5, 6, 7, and this guy 8, and this door 9.
Ooh.
You see, this door is also a system. What kind of loading do you have in this door? This is the first time we see that we didn't have it in electrostatics. What kind of loading do you have in this gate or door? Yes, you have normal hinge forces. You say pin, fundamental force in the pin or hinge. Remember that vectors. But also we have a distributed load come from the fluid. This is surface force, not body force. Body force is gravity. It's surface. You remember when we said surface, you walk over the dash line? This is the first time you have the surface force, a distributed load. Remember we gave you trapezoid and rectangle and so on. This time, nobody gives you that, but there is a distributed load. There is a trapezoid load. Here you have a pressure here, and then you go down a little bit, and the pressure increases. So you have a distributed trapezoid load. So if you, yeah.
Why is it a trapezoid, not a triangle?
Because, let me draw the figure here. So, let me set up the problem halfway, and then I'm going to make a homework so you finish it, get the number, and submit it. Right? The final value is just a numerical value. Right? It's not derivation, it's just a value for rate graph. So, this is my system. That's the first one, that's the gate. Right? So you're going to have a distributed load like this. Call it P1, P2. And then let's use a different darker color for loading. So loading, I'm going to use black for loading. Right? P1, P2. And then this hinge, you have how many moments do you have in the hinge right here? Of pin? Go back vector static. Can I move it in the x direction? No. Can I move it in the y? No. So you're gonna have ax, ay. Do you have a moment here, couple moment? I said problem is frictionless. So there is no friction moment here. Right? Then you walk over the border of that and you see there is another hinge called B that this arm is connected to. So that's point B. So here you're going to have dx, dy, and your opposite of that dx, dy, you have on the arm connecting up. What else do you have? FED. Nothing. That's a full FED for gate. And now for this guy, you have this, and let's take this point is CXCY. Is that the FED for arm? Or are we missing something? Can you tell me? I'm trying to find the FED for that.
The string.
I'm trying to draw a FED for this part. So what am I missing here?
String.
Yeah, the force coming from, who said friction? There's no friction. The force coming from the cable, this is the cable, right? The force coming from that, call it T. You see that? That's the full FED for the arm. And then you go to this pulley right here. So I'm going to draw it here. So the same T, call it T1, go up, and then T1 goes here, and then reaction here. Call it D, dx, dy. Guys, should I do these pulleys right here? Should I do this and this?
You don't need to.
What did we do in electrostatics? We applied the moment equation to the center and we proved that T1, whatever T, if you say T2, is same. As long as you don't have friction and mass, the force is conservative in a cable. It doesn't matter how many pulleys you have. So what I'm going to do, to save my time as an engineer, I'm going to just say this is just one T, this is just one cable. You see that? And it goes all the way to here. Right? Go all the way to here. So that's just one cable. So I start from here. I take that as system. I'll just save my time. So that's going to be the same T, right? And call this T2. guy is the same cable that goes all the way to there. See that? At some point, it's gonna go get connected to this one. So I'm doing a FED for this guy. This is a FED for that. TT, and then you have T1. Call this T1. Call this T1. And now I want to do a FED for this guy. What do I have? T2. T2, T3. And then I want to do a FED for the last one. Gonna be T3, T3, and T4. And then finally, a FED for the block, which is going to be T4. Right. Right? So system, FEDs, equations. I want you guys to write all the equations. What's the fastest method to solve this? There is a trick with just 3 lines. I said 3 lines. The answer to that is 3 short lines, not long lines. What's the fastest way to do that? Well, write moment about that, which is basically, I don't want you to do that, don't do the fast method. Go ahead and write all the equations. How many equations do you get here? 1, 2, 3, 4, 5, 6, 7. 7 system in 2D. How many equations do we have? 21. Write down all the 21. Even if the equation is null, 0 is equal to 0, write it down. And then solve them. You pick one equation, don't solve 20 by 21 system of equation. You can do that, but that's a computer method. We're not going to do computer method here. We do the fast method. Solve it and get the final value. Now here is the fast method. I want to just give you the fast method and finish. The fast method, well, those 21 equations, we're not going to solve all of it. We just select it. The one you select is the moment about this point. What's the moment point about this point? Well, you have the pressures. Right? You have the pressure here. What's the value of pressure here? You have the height above this point. Look at it. What's the height above that point?
8 meters.
The height above that point is 8 meters. And then you have, so it's 8 times the density of water, 1,000 times constant of gravity, G, time, so rho G H. That's the pressure here. What's the pressure here? Rho G times, what's the height of all that? 8 plus, yeah, this all the way from here to here is what? You say gauge length is equal to 1. So 1 plus 8 is equal to 9. So you have these two pressure, you can find the trapezoid distributed load, and then the centroid is where? Is below the centroid of that. And put the unit load, so you eliminate that and replace it with point load, exactly what you did in electrostatics. This is one way you can do that. What's the other way? Use the relation we developed. In the last class, we said you have gamma H bar A. You see for incline, you have the resultant force on it, you find the center of incline with respect to water center, that's going to be your H bar. Right? Now, imagine this incline is 90 degrees. Where is the center? Here. So find that H bar, put in the formula, you get the resultant force. Where do you put it? Y bar plus I X divided by Y bar A. Go to the last class, that's Y tilde. I draw that this equation from scratch, it's integral. So do not compute the centroid of that, which you could using electrostatics. You get identical result if you use this formula. So you get Y bar, 0.5 from here, but you go a little bit down. How much you go down? You need to get moment of inertia for that. What's the moment of inertia for that? That's it. This is a span of K. This is the height, H. So the moment of inertia with respect to the center is 112. Whatever the span is times H cubed. So you put it there, plus divided by Y bar, which is 0.5 times the area of that. You do that, then you find the point that you substitute the point force. So you get rid of this here, the point force. So I have one force known, so this force is known. This two is unknown. But if I write moment about that equation, which one am I going to get? Bx. So you get Bx. If you have Bx, the next equation is what? Moment about this point. What do you get? Tension in cable. Right? You're gonna get that. And then if you get tension in cables, you can get weight by dividing by factor of molecular. So do that and look at the homework and work on it and so on. Okay.
I don't know how to stop it without breaking
You
it.
go and watch, see the
It's
question.
not that fragile, I promise.
Not break the phone, but like break your